guys, Mr. C here, back with another TestTube video. So we're back again today with Stoichiometry, part 2, this time talking about limiting and excess reagents. Now, this is one of the most requested things as far as stoichiometry goes when we ask you guys what you wanted to see. So, what you ask for is what you get. We're going to talk about limiting reagents, talk about excess reagents, and through my years of studying, I have come up with a very, very simple way to figure everything out. So, here we have the reaction of ammonia, this NH3 here, and it's reacting with carbon dioxide to form this interesting compound here and H2O. So this NH22CO, this is in fact called urea. Now, it sounds exactly like where it comes from. It is present in urine. It's actually one of the main compounds present in urine, but it's actually also found in sweat too, which kind of can give sweat that weirdish sort of scent. Anyway, not the point. We're going to talk today about reacting ammonia and carbon dioxide to make urea and H2O. And we're going to have specific quantities of both of these reactants or reagents here. And we're going to see which one limits the reaction. Now, when we're talking about a reaction, just about any chemical reactions, we're not always going to have these things perfect. Chemists can only get so close to measuring out quantities of things that one of these two reactants is going to run out before the other one. Now, when that happens, that thing will be called the limiting reagent or limiting reactant. This means this is the reactant that will run out first. It is what is going to limit our reaction. It's going to hinder the reaction after some time. So, when we are talking about our limiting reagent, limiting reactants, first we should establish which ones are our reactants. And in this case, those two are the reactants. They are on the left-hand side of the arrow, of our yield arrow. And what we're saying is 2 moles of ammonia react with 1 mole of carbon dioxide to give us 1 mole of urea and 1 mole of H2O. These two react, and these two are produced. So, when we have a limiting reagent, that's the thing that's going to run out first, well, on the other side of that, one of these two is going to be in excess. It's going to be our excess reagent. So the excess reactant means we are going to have one of these two reactants here in excess, or left over unreacted at the end of this actual reaction, if we're actually to do this in the lab. So, let's begin with a question. We now have 2 questions that are being asked here. We're going to focus on this top one here first. Which of our reactants is the limiting reagent and which one is the excess reagent? Now, we've also been given 2 quantities here for our ammonia and carbon dioxide. We're saying that we are given 637.2 grams of NH3, and it's going to react with 1,142 grams of CO2. If we were to take both of these amounts of our reactants and put them into a flask or something and reacted them, which one is going to run out first? That's what we want to know here. Which one is going to limit our reaction? Which one is our limiting reagent? And then, of course, when we figure out our limiting reagent, we can figure out which one is our excess reagent too. So, sometimes you can look at the moles in front and kind of make a good guess. So you can take a look and see as far as the quantities that you're given, but I'm going to run through it mathematically, and this is a foolproof way to figure out every single time which one is going to limit our reaction. Now, what's really nice too is the method that I use. We're actually going to figure out our theoretical yield of our product that we're solving for here. So we want to figure out, the second question is, what is the theoretical yield of urea that we produce by reacting these 2 quantities of reactants together? So, let's find out. We're going to start with ammonia here, and this is what you're going to want to do every single time you start one of these limiting versus excess reactant questions. You're going to look at your products, and you're going to pick one of them. And sometimes it might be 3, sometimes it might be 4 products that you get, but what you're just going to do is you're going to pick one and you're going to stick with that one. So what we're going to do is we're going to use a little bit of stoichiometry, convert from grams of ammonia to one of these two products. Now, in the prior question that I had up on here earlier, is asking what the theoretical yield of urea was. So let's go ahead and solve for this one. So I'm actually going to convert my grams of ammonia to moles of urea. And I'm going to do the exact same thing with carbon dioxide in just a few here too. I'm going to convert grams of CO2 to moles of urea. And we're going to compare our answers and then kind of go from there. Alright, I have the ammonia set up, ready to go to convert it to moles of urea. Now, why do we need to convert it to moles of urea? Well, we need to convert it to one of the two products. And we could go all the way to grams of urea, but it's a lot easier just to stop at a mass to mole conversion. It's less steps, it's less stuff you have to solve for. So, what we need to do here is we take our 637.2 grams of ammonia, and we need to get that into moles of ammonia. The only way to do that is by dividing it by the molar mass, which I calculated for you already, and it's 17.03 grams per 1 mole. Or, if we flip-flop that equation, for every 1 mole of ammonia, you have 17.03 grams of ammonia. And so, with grams on top and grams on bottom, these cancel out. Now we have moles of ammonia, but we still need to get to our moles of urea. Well, the only way we can do that in this case is by multiplying the mole ratio of our product to our reactant, or in this case, urea to ammonia. We have to look at the coefficients in front of our reactant and our product here in our chemical equation. And for every 1 mole of urea you make, you use 2 moles of ammonia. So we put 1 over 2, or multiplying it by 1/2. So once we plug all this into our calculator, we actually find that we make 18.71 moles of urea, which I'm just going to make it uppercase U just because I'm running out of room here. So 18.71 moles of urea is what we get if we start with 637.2 grams of ammonia. Now, what I want you guys to think about here is, what I'm saying in this equation is I am starting with a limited supply of ammonia. And I'm pretending that I have an infinite supply of carbon dioxide. Now I know I put this 1142 right here, but for this top equation, we're going to go ahead and just ignore this number for right now. We're going to pretend that I only have 637.2 grams of ammonia to work with, and the entire universe's supply of CO2. Now, if we took all of those things and put them into a reaction vessel together, we would react 637.2 grams of ammonia. We'd react some quantity of CO2 that doesn't matter because we have an infinite supply of it. And from that, we would produce 18.71 moles of urea. So, that's what I want you guys to think about when you're looking at this very first one. Now, we're going to show you the other half of this. We're going to pretend like we have an infinite supply of ammonia. We don't care about the actual amount of ammonia, but we do care about how much CO2 we start with. So we're going to start off with a finite supply of CO2 and an infinite supply of ammonia. Essentially what we're doing is in this very first equation here, we're pretending like ammonia is our limiting reagent and that CO2 is going to be in excess. Now that we've solved the first portion of this for ammonia, we're going to pretend here like we have a finite supply of 1,142 grams of CO2 and an infinite supply of ammonia here. Now we're going to do the exact same thing. We're going to convert from grams of one of our reactants to moles of our product, our solved for product here, urea. So, we take our 1,142 grams of CO2 and just divide it by the molar mass, or for every 1 mole of CO2, it weighs 44.01 grams of CO2. And that is going to cancel out our grams on top and on bottom there. We're left with moles of CO2. Next, we're going to multiply by the mole ratio of urea to CO2, of our product to our reactant. And luckily for us, the coefficients in front of both of them are just 1. So essentially it's like multiplying this math function here by 1. So we're including the moles of urea over moles of CO2, the mole ratio of product to reactant here, just so that we can cancel units out. All I'm doing here is canceling out my moles of CO2 on bottom and on top. That way we're left with moles of urea in our answer. So, when we do this and go through the math in our calculators, you should get 25.95 moles of urea. And that is the answer we would get if we had a limited supply of CO2 and an infinite supply of ammonia. Now, what I want you guys to do is I want you now to look at both of your answers. I want you to compare these two. And remember, this top one up here in blue is just saying if we had a limited supply of ammonia but an infinite supply of CO2. And the bottom one here is saying the exact opposite. If we had a limited supply of CO2 and an infinite supply of ammonia. So, which one gets you the smaller quantity of your product? When we are comparing our two answers here, the one that gives you the smaller amount of product is going to be your limiting reagent. That means ammonia, in this case, is our limiting reagent, because it produces the smaller amount of our product. Whereas CO2 is going to be our excess reagent. There's going to be a little bit left over in our reaction flask, which is okay. But what this essentially means is that if I took that much ammonia and this much CO2, put them into a reaction vessel together, reacted them, we could only make this much this much urea. We can only make this much urea. NH3 is our limiting, CO2 is our excess. And it works like that every single time. If you take both of your reactants, convert them to moles of one of your products, pick it and keep it the same, the one that gives you the smaller amount of product will always, always, always be your limiting reagent. And the one that gives you the bigger amount of product is always going to be in excess. So what's really cool about this is that now we can do two things. We can go ahead and ignore this whole bottom part here, because this is what would happen if CO2 was limiting and ammonia was our excess. So we can ignore this stuff in purple down here. This is our main equation that we're going to use for future stuff. Now, because ammonia is our limiting reagent, and if we took these two quantities and reacted them together, this is theoretically the largest amount of our product that we could make. I can't make anything more than this. I cannot make any more urea than this. This is it. That's it. We can't make 25.95, I can't make 18.72 moles, I can't make anything more than 18.71 moles of urea. So, that means that this number here is our theoretical yield of urea. So, this helps us find out three things. It helps us figure out which one's our limiting reagent because it produces the smaller amount of product. Which one is our excess reagent because it produces a greater amount of product. And it also tells us what is our theoretical yield of the product we're looking for. If I took these two quantities of reactants and actually reacted them, this would be our theoretical yield, is 18.71 moles of urea. Now another thing that some students get a little confused is they'll say, oh, our limiting reagent is urea. No. Our limiting reagent has to be one of these two things. It cannot be a product in this case. Or sometimes what they'll say is, oh, the theoretical yield of ammonia is 18.71. Again, we can't say that because we're not looking for a yield or an amount produced of ammonia. We are reacting this much ammonia to produce the urea. So don't get those two things confused. I know it's very easy to, but that's why I like labeling everything, because if I'm going to go ahead and say, oh yeah, my limiting reagent of urea is 18.71 moles, I'm going to look at that and go, wait a second, no, it was 18.71 moles of urea produced. That can't be our limiting reagent because it's a product. So keep those things in mind when you're writing it out. We want to keep our units in order here. That way we don't get confused with moles of urea or moles of ammonia. Let's say we actually did this reaction in the lab. We actually started with the two quantities of CO2 and we produced some amount of urea. We might be asked to then figure out what's our percent yield of this reaction. So what I've done here is I've kind of wrote up a few notes here to keep in mind here that our limiting reagent is ammonia, excess reagent is CO2, but we can make from these two here a theoretical yield of urea of about 18.71 moles. So we have another equation that we can use here to kind of help us figure out a percent yield. A lot of times on tests and quizzes and homeworks, an actual yield or a percent yield will be asked to be solved alongside of your theoretical yield. And now that you know how to solve for a theoretical yield, figuring out the other two is actually just a matter of some simple algebra. And I guarantee you guys have done a question or done a calculation like this on your own. So let me pose another question for you before I get to solving a percent yield of urea. Let's say you took a quiz or a test. Let's say you took a test. And you scored on this test out of, let's say 150 points. Let's say you scored 112 points. That was your score on the test. How can you figure out your grade percentage from just these two numbers here? It's pretty simple. In order to figure out your grade percentage in this case, you're going to take your actual score divided by the theoretical score that you could have gotten on this test and multiply it by 100. So you just take 112 divided by 150 times 100, and that's going to give you a 74.6%. We can kind of think of this. Your score that you got on the test is like the actual yield from running the experiment. It's what you actually wound up getting. The total you could have gotten on the test is like your theoretical yield in running the experiment. Theoretically, you could have gotten 150, but in actuality, you only got 112. And doing the math really fast to figure out the percentage, this is your percent yield. This is the percent of points that you actually got. So, we can actually apply this to a question talking about what's our actual yield and what's our percent yield of the reaction of ammonia and CO2. So this is the equation that you are going to use in this case to figure out your percent yield given an actual and a theoretical yield, and given 100. Now, we can actually rearrange this equation if we want to. Let's say we found a theoretical yield and we're given a percent yield, but we want to know what our actual yield was. Well, we can use some algebra really fast to rearrange it. So the next question I'm going to be asking is, I'm just actually going to only be looking for a percent yield given an actual yield, and we're going to use this theoretical yield right here. So, let me set that up for you guys really fast. Alright, so now we've been given an actual yield of 6.571 moles of urea. All we need to do in this case is just plug things into this equation and run them through our calculators really quickly. Plugging in the numbers, we say our percent yield is equal to our actual yield of 6.571 moles of urea divided by our theoretical yield of 18.71 moles of urea times 100. Now if you run that through your calculator, be sure what you do first is this division first. Divide your 6.571 divided by 18.71 first. You don't want to do too much all at once because it might confuse your calculator a little bit. So, do that division first, and then multiply it by 100 to get a percentage, and what you get out of this is 35.12%. But if we actually ran this reaction with those two initial quantities of ammonia and CO2 and got out of it 6.571 moles of urea with a theoretical yield of 18.71, the best that we did in this reaction is just a 35.12% yield. So it's not that good, but a lot of times in chemistry, that's really all you can hope for is getting a 30% yield or a 50% yield. Not every reaction you're going to get 100%. In fact, you probably will never get 100%. If you get 100%, you probably did something wrong or have some contamination going on. So with actual yields, the only way we're going to ever have numbers for those is if we're solving for it. In this case, you're always going to be given a percent and a theoretical yield. Or if you actually do the experiment itself and come up with an actual yield via experiment, via actually running this reaction. Alright, thank you guys so much for joining us today in our talk about stoichiometry. Next video we're going to have is going to be part 3, where we're going to talk about percent composition, empirical formulas, and molecular formulas as well. Like, comment, and subscribe down below. And check us out on Instagram at TestTube Science, where we try and do daily posts about cool science things in the news or in daily life. Alright you guys, thank you again for joining us. We'll see you in the next video. Bye! TestTube video talking about stoichiometry.
You don't seem excited at all.
So I'm not talking super duper high pitched. Don't tell me to smile. I can't talk and smile at the same time. It doesn't work for me. Questions, son of a gun.
Because it's loud.
Yeah. You're distracting me, stop it.
I'm telling you to sweat and urine.
I didn't even know what you meant by that. I thought you were doing like a Michael Jackson thing or something.
Okay.
Like, what are you doing back there, dancing? Something? Just dancing around? So, urea.
Come here, river.
Jerk.
Oh, can you see the first double bond at the top?
Dang
It's
it.
like smudged.
Yeah.
It looks like a mountain now. That's good. That's good. Don't touch it anymore. Stop it. Now it looks worse. Make that little bump go away. So your handwriting, like, is it sloppy because you don't try?
Otherwise you
It
can't
can move
read it.
over 3 inches to the left.
What?
The poster can move 3 inches to the left.
Can move 5 feet that way.
Or is that like
No,
you
I'm
trying?
actually trying.
Your handwriting is just that.
Yes.
Okay.
Yes, it is, because I never really practiced it when I was younger. Okay, so I've set up. What?
You said, okay, so for every single clip so far.
You do it then. I'm done. I'm gonna go to sleep.
Honey.
Good night. I don't think it's that bad. I mean, it's for the most part legible. Like what? Are you having a hard time reading the ones or something? Is that the issue here?
No, it is.
What's wrong?
It just looks sloppy.
I like to think I write in like Comic Sans kind of, where it's legible, but you don't like looking at it. That's what happens when they force you to write in cursive in elementary school and then tell you you're going to use cursive for the rest of your life. No, I'm not.
You're doing great.
I did the thing. Do that little thing all the time.
Yeah, you do.
All right, so I got pneumonia. Now I've written up here.
Don't say I never did anything for you.
Yeah, like that one time you forgot to hit record. I'm kidding. I'm just complaining and complaining. And yes, kids, this is straight vodka. We party like that. Here, I'm pepping out. Alright, get back. Look your outlook. Read your book. In this case, I'm going to be giving you some. I don't know.
It's gonna be really hard to edit.
It's not. You just gotta. I'll edit it, whatever. Then you can.
Then I'll do my hair one.
Yeah, and then you can look at my finished product and tell me it's crap, and then do it yourself.
Typical.
Just like if you put flames on the side of your car, it goes faster.
No, it doesn't. It just looks bad.
No, it totally does.
It just looks ghetto.
Don't ruin my dreams. Alright, so looking at... like bounced. Like I felt it like through my body. Okay, so try not to say that. It's just so easy. Last time I used cursive.
Okay, get on with it.
The last time I used cursive was to write that stupid paragraph on the back of the SAT. Thank you for reading Magic Carpet. We hope you enjoyed your flight. Goodbye, 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 goodbye now, goodbye.